My name is Professor Joseph Wunderlich, and I am a professor of engineering, computer science, and architecture of buildings. Um, this is a lecture on power, and firstly, we want to just understand what's coming out of the wall. The United States is 120 volts. It can be 110 or 115, depending where you're on power grid. It can be typically 240-ish in other countries. And there's reasons for that. It's a little more unsafe to transmit at 240, but your I squared R, current times resistance square losses, are less, so it's more energy efficient to transmit at higher voltages, but less safe. So it's a judgment call what you want to do there. Anyway, we have 120 volts coming out of the wall. You have both current and voltage in sync. That can shift one way or the other. The current can be out of phase with the voltage if you have reactive power of inductance or capacitance. We'll just touch on that a little bit in this lecture. You have to transform this AC voltage down to to a lower voltage. The chips need typically 5 volts if it's bipolar TTL kind of transistors, or CMOS 3.5 volts, or you might need 12 volts for your motor. You do need 12 volts for your motors and your drives, your optical drives and your magnetic drives are spinning, not your solid state. Also, your fans need 12 volts. Then you need to rectify, so you need to make it not alternating anymore. It has to be just a flat voltage level. So you either get the zero voltage would be grounding, equivalent to logic 1 for binary, and then your 5 or 3.5 volts high level constant levels would be, and direct current would be for logic 1, and that's what you feed your motherboard. Now, continuing on power, these are some standardized notes from when I was a professor at Purdue University, a big university with as many as 7 or 8 people teaching the course at any given time across all the branch campuses also that were not autonomous. So committee established these notes, and then you see my handwritten notes over top of it. So we talk about clean power now, and the reality of you have 70 disturbances a year typically. Customers can have problems with external plants. So I have some experience building buildings. My bachelor's degree is architectural engineering in 1984 from the University of Texas in Austin, and it allowed me to get, if I wish, licensing for engineering or architecture. So what you see, and these notes are when I went back, master's, PhD, IBM research, professor at Purdue University, teaching power in this particular course. But I mentioned that because I needed to understand this particular topic when I was building buildings too, including high-tech office parks in Texas and California, in charge of building raised computer floor rooms. So with heating and cooling needs, cooling more importantly actually at the time, I don't want to get on a tangent with that. Voltage, so categories of power problems, you have variations in interruptions, transients, which are temporary, and starting up systems, robots or whatever, motors. The startup phase is a transient, and then steady state is after the transient, but you can have problems with some harmonics with the waves, different causes. Also, you can have wire grounding problems. What you see here are my review notes that I purchased when studying for the professional engineering fundamentals licensing exam that you take when you're a student. So I took that and passed it in 1983. And I just thought this would be a nice thing to compare the analogy between mechanical and electrical and fluid and thermal. So to help you better understand, electrical current is sort of like fluid flow. The analogies don't hold everywhere, and voltage is sort of like a fluid pressure. And I always thought that was nice, but I've had education all over the place in electrical, mechanical, architectural. And so I like the analogies perhaps more than some people. Also, you do want to understand here before we proceed, power, P is in watts, R is resistance measured in ohms, and then here's some basic formulas you should know. Voltage equals IR, voltage equals current times resistance, and power equals I squared R. That's current squared times R, which also equals IV. And I could tell a whole story here of why you transmit at higher voltages in Europe and other places, because you have less I squared R losses. Yeah, it's more energy efficient. However, it's more dangerous if you have 240 volts going into your every house outlet. Here's just a little more of the analogies here that from the book, and again, I like to look at things like this, comparing electrical, mechanical, thermodynamics, and fluids. I've had courses in all that, just like the mechanical engineers. A ton of structural and a sufficient amount of electrical and architectural engineering to understand what to do to build buildings, and then, of course, a great deal more for master's and PhD in electrical and computer engineering. And again, some more analogies. So you might want to stop and take a look at this. Before we move on from here, professional licensing is important for anybody dealing with the safety of the public. Structural, of course, it's critical. Things fall down and kill people if you don't do that right. Electrical power, yes, that can kill people. Machinery, yes, mechanical is needed for sure. Architecturals fall into those categories, yes. Electrical, other than power, was questionable for a while. Control systems, big machinery can kill people. What about computing? For a long time, it was debatable. But now, I don't want to give a whole sermon here, but the artificial intelligence and autonomous systems controlled by computer engineering decisions and designs can kill people. So I encourage all engineers, including computer engineers, to seriously consider getting licensed. You get it's a process. You got to first pass the fundamentals exam, spend 4 years under a licensed architect, or be a professor too. And I could certainly take the exam now if I wished for professional licensing. And then you get this stamp. And then when you stamp drawings and designs, you're now assuming liability, which you might want to be careful with, because you will get sued if people get hurt because the system that you stamped drawings for fails. But you get paid quite a bit of money by people to assume that liability and that supervision. So you should consider it. Even if you don't practice as a professional engineer, if you have an ABET accredited degree, undergraduate degree, like computer engineering is at Elizabethtown, and the other engineering degrees, then you can get licensed. If it's not ABET accredited, you can't get licensed. Now back to these Purdue lecture notes from a course I was teaching on power and controls. We actually combined into one course. We want to look at the different things that can happen or that you want to control, design around, or mitigate when you're specifying clean power, or asking a consultant to do that for you. So this is, IEEE, Institute of Electrical and Electronic Engineers, setting standards in all kinds of electrical things, including computers, certainly power. In terminology, in IEEE terminology, this first thing is interruption or a dropout, also referred to as an outage. So, total loss of voltage for some duration. So this, we all understand what that is. You lose your power. Now the next thing, maybe not quite as common to understand, is a transient, so a temporary startup of something, a surge. So you see voltage over time here, and some causes. So initial energizing of power faction correction capacitors. Now that, to fully understand, takes some more lectures and other courses. For electrical engineers, power engineers, they should certainly understand that. But what you have is real and reactive loads and reactive loads of inductance and capacitance in it. The real is pure resistance. It doesn't cause problems. But when you have inductance or capacitance, like motors in a factory, you have inductance, and then you want to cancel out the negative effect with capacitance if you have too many inductors, motors. Because what happens is your voltage and current get out of phase with each other and messes up the delivery of power. And so, and the power factor is an angle between the phasors that represent the two sine waves of the current and voltage. the angle between those two vector representation, phase representation of the sine waves. So if you understand sine waves and phasors in current and voltage, that makes sense to you. If not, don't worry about it. Hire a professional electrical engineer to do your power thing, especially if you need a bank of capacitors in your factory to cancel out the power factor problems because of the inductance of your motors, which you get penalized for, by the way, from the power company when you're in the cost, the rate that they charge you. So that's for another lecture. Also, switching transmission lines. There's substations. There's big giant switches. At Purdue, I took students on field trips. These are big science fiction looking switches, some of these things. The big giant ball that swings on the end of an arm that connects to super high voltage at a substation. Otherwise, it's going to arc across. And just simple switching, like you would see a circuit breaker kind of thing, a smaller scale. So that those are little blips that can happen as cause a surge, and a surge can blow out a circuit. In olden days, when even static shocks would blow out your circuits. One reason putting bipolar transistors around the rim of your chips and CMOS in the middle is the bipolar could handle the shock. Where your pinouts are. That's not quite an issue anymore as much, but still, you don't want a huge surge coming in. That'll blow out even the most recent of chips. Next, we want to consider a sag. So that's just a small drop in voltage, and you're saying, well, that can't be a problem. Well, yes, because everything inside the computer is actually not digital. It's made to digital, but when you have capacitance charging up on a gate or on a signal line, that voltage isn't always going to be exactly 5 volts. Especially if you have fan out, where you have one thing circuit driving a bunch of others, your signal degrades. And if you've got a drop in your initial power to the machine, you could have bit errors and the thing just not functioning. That's some of the worst kind of errors, where it's intermittent, and so you don't want a sag for your computer. Also, a swell. Next thing, you don't want to see that, and so you see the arrow here, a fault. We have a short circuit. We have temporary, like a short, where somebody does something stupid and gets a short circuit or overloads an outlet or something. At first, you'll have a sag, and then the breaker will trip, which will cause a swell, and then then shut off. So you have to filter out these things. Is essentially what you need to do for clean power. Now, this here is a graph from the Information Technology Industry Council, which is part of this CBEMA society. And so this graph, which on the next slide I have the actual graph from the society, or from the council, and describes a little more. But what this does is it looks at each, you'll see each of the different things, solid state tolerances, swells, surges, high frequency lightning, under voltage interruption, and then how long you can handle that on the x-axis. So you see on the y-axis voltages varying around a baseline voltage that you want, and so how much can you withstand? On the next, you'll see on the next page a little more detail of describing this. So I'll wait till we get to that next one. And then lastly, before we go to that next slide and look at the details of this ITIC curve, we talk about harmonics. So Fourier series components, waves, wave interference, what can happen is you have AC power being delivered to your building, to your computer rooms, and then if there's a factory nearby or other sources, generators and things, there's harmonics that can come across the power grid, and waves superimpose on each other, creating problems, right? If you know wave theory, resonant frequencies and things like that. So that's something you have to monitor too, and control, not just monitor, but filter out and mitigate. Now here's the actual graph, the standards that a professional electrical engineer will write specifications for the contractors to bid on, and that will ensure the computer company and you as a chief information officer for a large company perhaps that your computers will not fail under different circumstances. And so you see each of the things here, 1, 2, 3, 4, 5, 6 that we've discussed, and how to how to specify allowable variations or mitigations to things that can happen. So what you see on the right hand side here, it says 120 volts written in red. That's the RMS, or root mean squared, the voltage that you want to have as your baseline, what you're expecting. Now you can handle a certain standard deviation from that without any loss of function. And so what you see now on the x-axis is the duration that you can withstand a certain problem. And so you can see that there's no limit to how long you can withstand going down to 100 or go up to 132 volts, or down to I guess what's 102. It's sort of hard to read that, but plus or minus a certain amount of 10% or so for unlimited period of time. Now, what you see in some of these other things is, and I don't expect you to know every detail of this in an introductory course, but let's see. So let's start, and so, well, just look at all the different things. We'll start at the very top here. Let's look at high frequency surge up there. So you can only handle a very small amount, and these are on milliseconds, I believe, down the small scale here. Yeah, on the x-axis. So you can only, you can't really handle a surge at all if it's a lightning strike. But you can handle certain voltage, high voltage surges up to a certain amount. So you can see there, I said high frequency surge lightning. That's plus 5,000 or 500% equals 600 volts for 10 to the negative fourth of milliseconds. So 100 microseconds. But you want to avoid the joules of energy. Joules is the voltage times the time. So, like if I put up an electric fence around my farmland here, and there's many thousand joules, but it's many thousand volts, but it's such a short period of time because joules is voltage times time. And so, you take a look at all these things. Don't try to memorize all of them. Just realize that all these characteristics are kind of represented on the same graph here of how long you can withstand a certain one of these problems. And you want to have a system designed to handle that.